Hi, my name is Oktay. Welcome to today's video about the chemistry of the element phosphorus. This is a nice painting of German alchemist Henning Brandt. Phosphorus has the atomic number 15. It was discovered in 1669 by Henning Brandt. During that time, he was experimenting with evaporation products of urine because he was searching the philosopher's stone. And the name of the element phosphorus comes from Greek mythology, from the Greek word for light bearer. This is one of the allotropes of phosphorus. Allotropes are different forms of the same chemical element. That's white phosphorus, P4 molecule. The bottom left corner, this fresh cut piece of white phosphorus, so it's a yellowish color. At the right, you can see the structure of the P4 molecule. That's a tetrahedron structure. But the structure has a ring strain because each phosphorus atom has 3 electron pairs. So the tetrahedron angle is 109.5 degrees. But in a regular triangle, the angle is 60 degrees. However, there's a trick to reduce the strain. That's by bending bonds. So atomic bonds can be bent. This means that the electron density is not along these edges, but above this. So the bonds are bent, and that's one way to partially compensate this ring tension. But still, the P4 molecule is very reactive, and you can store it under water. These are the allotropes of the element phosphorus. At the bottom left, that's white phosphorus. If you heat it over 280 degrees, you get red phosphorus. At higher temperatures, you get violet phosphorus. And at high temperatures and high pressures, you get black phosphorus. These are the 4 allotropes of element phosphorus. This is a picture of red phosphorus. It has an amorphous network structure, and that makes it less reactive than white phosphorus P4. This is the structure of violet phosphorus. It is made from red phosphorus at higher temperatures and has a lattice structure. This is black phosphorus. It is made from white phosphorus at high temperatures and high pressures. This is the least reactive allotrope and has a pleated structure with sheets of atoms like graphite. There's one difference to graphite. The graphite is made of flat sheets. Black phosphorus, the sheets are not flat. But still, it looks a bit like graphite, and it is conductive like graphite. This is the nucleosynthesis of the origin of the chemical elements. Phosphorus is a member of the nitrogen group here. Fifth main group of the periodic table. Its origin is from exploding massive stars and exploding white dwarfs. This nuclear reaction is called oxygen burning, oxygen fusion. It requires a minimum temperature of 1.5 billion Kelvin and a minimum density of 10 to the 10 kilograms per cubic meter. In nature, there's basically one isotope, that's the isotope 31 phosphorus. There are 2 more radioactive isotopes, 32 and 33, but only in traces. Phosphorus is an essential element for life. For example, it is one of the 2 components of the backbone of the DNA molecule. The other one is deoxyribose. This is the diagram of the abundance of the chemical elements in Earth's crust. You can see phosphorus is in number 11, quite abundant here. About the same, almost the same as carbon. The human body contains 700 grams of phosphorus, and 85 to 90% is in bones and teeth. If you're interested in the structure of bones, you can check my calcium video. Yeah. These are 3 examples of phosphorus minerals. At the left, that's apatite. That's calcium phosphate, fluoride, chloride, hydroxide from Madagascar. In the middle, that's phosphorite. That's phosphate sediments from Erkai-kun in China. And at the right, that's vivianite. That's iron 3-phosphate octahydrate from the Morocco Cala mine in Bolivia. This is how you can make P4 white phosphorus. That's a carbothermic reduction of phosphate minerals in an arc furnace. That's the electric oven, the furnace. These are the electrodes, coke electrodes. This is the chemical reaction, calcium phosphate, fluoride plus silicon dioxide plus carbon. You get P4 white phosphorus, carbon monoxide, calcium silicate, and calcium fluoride. P4 is travels here, then you get rid of the dust. And the last step is to separate the carbon monoxide, and the P4 is collected under water. This is one important use of phosphorus. That's as fertilizer. At the left, that's a picture of triple superphosphate. This is monocalcium phosphate, CaH3PO4. And at the bottom, you can see the development of the fertilizer prices in recent years. Triple superphosphate is here at recently 600 US dollars per metric ton. And you can see that in recent months, the prices went up. For fertilizer, you need a high content of phosphate, and the fertilizer needs to be soluble in water. And the triple superphosphate fertilizer meets both these requirements. This is a picture of the rock phosphate reserves in the world. You can see Morocco is number one. There's 50 billion tons of reserves. China is Finland, South Africa, Russia, Jordan. This is the annual world production of phosphate rock. In 2020, it was 223 million tons. And there's this word peak phosphorus, which means a peak situation with the production of phosphate. And some experts predict this could be in the year 2030. And can this be a problem? Yes and no. So if yet continuously business as usual, then of course it will be a problem. But that's not how the world works, because there's technological progress. We need new methods to use resources more efficiently. For example, recycling from sewage. And there are new agricultural techniques, for example, limit erosion of the land. Or, in my opinion, another solution is vertical farming. This is a historically important fertilizer. That's guano. That's the excrements of seabirds and bats. They contain nitrogen, phosphate, and potassium. This was a natural fertilizer. When the Haber-Bosch process, the synthesis of ammonia was industrialized in 1910, guano was replaced by this process. Now you can check my nitrogen video if you are interested in how this works. Yeah, that's the story of guano. Guano was important in the 19th century, for example. This is a phosphate bead test. That's a simple qualitative analysis in inorganic chemistry. For this, you need a magnesia stick. You heat it with sodium, ammonium, hydrogen phosphate tetrahydrate until you have a 3 to 4 millimeter sized bead. Then you add your sample and heat it again to make the phosphate. The point is, different metal salts make different colors of phosphates. At the top right, you can see some examples. At the left, that's silver. You get a light yellow phosphate bead. And with copper, green. Nickel, orange. Iron 2, you get a dark green. And with manganese, you get a pink phosphate bead. And some of these ions make different colors in the oxidation and the reduction flame. So you can use this fact for a cross-check. At the left, this is the structure of a flame. This is the reduction zone of the flame. And at the top, that's the oxidation zone of the flame. This is a picture of safety matches. They were invented in 1844 by Gustav Erik Pasch from Sweden. And the innovation was the striking surface that contained red phosphorus. Red phosphorus is less reactive than white phosphorus, P4, which makes this matches safer. So with this innovation, the dangerous white phosphorus P4 was eliminated. And the main component of the match is the compound potassium chlorate KClO3. This is the structure of phosphoric acid, H3PO4. Concentrated phosphoric acid is a 85% solution in water. 90% of the production goes to the production of fertilizers, but you can also make soap and toothpaste. At the left, this is a chemical reaction of how you can make a normal phosphoric acid. That's a reaction of phosphate salts with stronger acid, sulfuric acid, for example, hydroxyapatite, H3PO4 plus sulfuric acid, you get 3 molecules phosphoric acid, plus calcium sulfate, plus water. Phosphoric acid is also used as a food preservative and in soft drinks. But for this use, you need phosphoric acid with higher purity. So this kind of phosphoric acid is made from white phosphorus, P4, via oxidation to P2O5 phosphorus pentoxide, and then adding water. This is the structure of the molecule ATP, adenosine triphosphate. This is the energy molecule in the organisms. The energy is stored in the phosphate groups here. It exists in the cells as a magnesium complex. Every day, 69 kilograms of ATP is used. So that's almost as high use as that's almost as much as the weight of the human body. So this means same ATP molecule is recharged again and again many times. At the bottom, this is an example how this ATP molecule is used. That's in C3 plants. These are the most common types of photosynthesis. They are called C3 because they need 3 ATP molecules for the assimilation of one carbon dioxide, one C1 molecule. So for the production of one molecule glucose, C6, H12O6, the C3 plants need 18 ATP molecules. This is a nice picture of the crystal berlinite, which is aluminum phosphate. This is in synthetic crystals. This is a picture of the chemoluminescence of white phosphorus P4. That's oxidation of P4 in the air, in the gas phase. And this chemical reaction to oxidation to phosphorus pentoxide makes the glowing light, and that's chemoluminescence. This is a nice picture of turquoise, which is copper aluminum phosphate hydroxide tetrahydrate. This mineral is from the Bishop Mine in Virginia, USA. That was today's video about the chemical element phosphorus. Thank you for watching. Have a nice day. Bye bye.